Thanks, Benoit. Before I start, I first want to thank Shmuel and Eran for organizing this absolutely phenomenal conference and for having me here. It's a great honor. And secondly, I'd like to acknowledge the birthday boy. It is a birthday after all. And you can't go to a birthday without bringing a present. I was one of Eran Sharon's very first graduate students back, I think 2004, 2005. And Eran Sharon, in turn, was one of Jay's very first graduate students. So that makes me one of the oldest academic grandchildren of Jay. And I hope it's not too much of a disgrace that I'm a theoretician.
Okay, you belong to Victor. You started it all.
So I do things usually with a pen and paper, and I think, and that's it. But occasionally I like to think with my hands, and I have this tinkering lab. And then I thought, well, what did I take from J Labs? And just by proximity and having seen Shmuel and Eran work for all this time, and what has gone with me since then and up until now. And then it dawned on me, and the answer is it's duct tape. So I think that most of all, I've learned that when an experiment is done good, it should all be automated and streamlined, and you should push a button, and data should flow to the computer. But that button has to be duct taped on. So with this, I want to give you this present. Now, I didn't have glass, so I made this out of PMMA, and it's hard to break. So I made a little notch. I don't know if you know, but it really helps the crack propagate. Okay, so there we are. What I want to tell you about today is things that actually started about 8 years ago while I was still a graduate student with Eran Sharon. And this is where we made this thing. So this silicon rubber conical structure is actually 8 years old. It's a very resilient structure. It's almost as good. I think it is as good as it was to begin with. And we were really intrigued about the way these objects lose stability. So this work was started back in the day when Yochai was still an undergrad student. Still an experimentalist and an undergrad student. And this is where we did the initial studies of these. But we didn't get really far. Yochai went to Weizmann, I went to Chicago, and then the system lay dormant for about 6 or 7 years until Erez Urbach arrived, who's here in the crowd, and he picked it up, and essentially everything I'm going to show you here today, from theory to simulations to experiment, is his doing. So all the hard questions, please ask him. So what are we looking at? So it's a very different mindset from the previous lectures. What we're going to look at is no microscopy, just the continuum limit, and no plasticity. So we're talking about dissipation in elastomers that are fully cross-linked. So these structures do show some dissipation when you torture them, but then if you let them recover for a day, they go exactly to where they started from. And the way these structures lose stability is actually quite intriguing. You can take a tennis ball, and if you cut it to the right size, and you invert it, and you put it on a table, it takes it about a second, and it pops. Now, the elastic timescales of these structures are about a millisecond. It's relatively reproducible. And flexural waves are much slower, and they take about hundreds of milliseconds. But this took a second. And if it's not convincing enough that this is not an elastic phenomena, I can take it and hold it in my hand inverted. And now as I age it, invert it in my hand for a longer time, and then I put it, it takes it longer to jump. So now comes the question of how far can you go with it? Can I actually make this jump really, really long? Or does it always pop after a finite amount of time? If I let you watch this movie and measure the creep, can you tell me if this is going to pop or not? What if I tell you the material properties of this and the geometry? Would have you been able to predict this motion? So this is what we started, thinking, and it took us a while to understand that we don't understand the system. So I'm going to start by showing you that, And then we realized that there is a very intuitive way to think about this type of viscoelasticity, and it goes through temporally evolving rest lengths. And this is essentially the story I want to tell you. So the main traits of viscoelastic solids are two, and they go by the name of stress relaxation and creep. Stress relaxation is what happens when you take these structures and do an experiment of constant displacement. You measure the stress, and the stress, as time evolves, partially relaxes. Now you can take the same elastomer and take it out of this setting and do a constant load experiment, and you would see that there's a creep for the displacement. The simplest model that is able to show both of these properties is called the SLS, the Standard Linear Solid Model, and it's sort of a marriage of the Maxwell and the Voigt model. It has two springs and a dashpot. The dashpot is connected in series with this spring that has a stiffness beta k, and in parallel to the spring that's here that has a stiffness 1 minus beta k. If I now abruptly tense this structure, the dashpot doesn't really have time to respond, and both of these springs elongate by the amount I pulled. So now I have a resistance beta k from this guy times delta x, and 1 minus beta k from this guy times delta x, and I see effectively a spring with a spring constant of k times beta, of k times delta x. Now, if I hold this thing at a constant displacement, gradually displacement moves from the dashpot, from the spring into the dashpot. If I wait infinitely long, then all the displacement here is absorbed by the dashpot, and all the force is supported by this right spring. So I started with k delta x, I end up with 1 minus beta k delta x, so I lost a fraction beta of my force. So this is what characterizes the system. We can write the equations of motions of it. Essentially, I have the force as a function of the total length I observe here, of the rest length of the right spring, the rest length of the left spring, and the length absorbed by the dashpot. So I have to know quite a lot about the system, but I also know how the length of the dashpot evolves in time because of force balance between it and the spring. So there's this ODE that if I know the appropriate initial conditions for it, I really can solve. But it doesn't really give me a lot of intuition as to how do I see a structure composed of these constituents and say this is going to be stable, this is going to be unstable at a finite time, at an infinite time, and those type of questions. What we realized is that if we now do an abrupt displacement increment, so say it has been doing something for a while, I don't care what. Now I take the system and I abruptly add another delta x to it. You can show quite easily that your stress increment or force increment grows by k delta x. So stress increments look like a standard spring with the same k. So why not look at it as if it is a standard spring with a spring constant k, however, something changes over time, and all these changes are going to be absorbed by this temporally evolving reference length. So now all of this thing is described by this thing. It's a spring, a standard spring, constant coefficient, temporally evolving rest length. Now when you do that, you automatically get what the rest length, temporally evolving rest length, should look like, and you get an evolution law for it. And the nice thing about the evolution law for this structure is that it gives you a decoupling to two distinct terms. L bar dot, or L bar, the instantaneous reference metric, reference length, evolves towards L, which is the present state of the material. That means that if I tensed it, it sort of tries to go to this displacement I gave the system. However, there's a simultaneous evolution towards this quantity, L bar naught, which is the state in which it was born, the state that if I relax the system wholly and let it go back to how it would like to be, it would approach this state. And these two terms compete in everything I do. Okay, so it's important to note that this is a tautology. All the information contained here is contained here. I lost nothing, but this gives me a very intuitive way of approaching this problem. If I now take a rubber band, then to begin with, L equals L bar naught. Now I do a sudden displacement, L bar naught is the same. It does not change. It never changes. L is here. L bar gradually evolves towards L. So it started here and it evolved towards L. Now say I leave the system. I leave this rubber band. It snaps back. But where does it snap back to? It does not snap back to L bar naught. It snaps back to the elastic portion. It snaps back to L bar. However, now together L and L bar evolve towards L bar naught. This evolution is quasi-static. It's done with the slowest time scale of the system. This now allows us to start examining instabilities in these systems, because now we can take all the things we understood for a single one of these and make them in an unstable configuration. So this is the von Mises truss, one of the most basic structures that exhibits bistability. And we have two spring coefficients here, K2 and K1. And let's choose the rest length of the system such that this red point, at this red point, the system is fully at rest. If K2 is extremely large, this is the only stable solution of the system. However, if K2 is sufficiently small, there's another stable point, which is somewhere down there. Okay? Imagine that in the limit of K2 going to 0, these two points are exactly identical. So we say, hey, okay, now we can just take this evolution laws we have, let the system evolve, and ask, can we take this system, put it in this metastable state, and allow viscoelasticity to take us out of it? So we do that, and what we plot here is the elastic portion of the potential. So this is not an energy governed system because there's dissipation. But in every moment in time, we can think of a potential that the force is the gradient of that potential. So this is as a function of the z location of this point, the elastic potential of it. So you see that there's this well, which is up here, and there's this well, which is down there. I take this thing, I put it down there. This is the red curve. Now I let the system evolve. And it turns out that what it always does is makes the well deeper. Viscoelasticity, once you got from a stable solution to another stable solution, will never get you out. Now, this is rather graphic, but we have this as a proof, and we have this to actually a more general setting. So this is where we understood we don't understand the system. And only once we finished proving that this is completely general, we sought another solution. And we realized, well, if stable states never pop, it means that the states that pop after a finite amount of time have to be unstable to begin with. But, you know, they're not completely unstable because I put them on a table and it takes them a second or 2 or 5 to jump. How could that happen? So now I increase K2 such that the red curve is unstable. But when I do this thing, I actually overshoot. I always overshoot. When I overshoot, I relax the system in its inverted state. When it's relaxed in its inverted state, it can actually acquire stability. It changes this potential constantly because you change L bar, you change these reference lengths. And once you change them enough, this point could acquire stability. It turns out that acquired stable points could be lost in time. As a matter of fact, you can show that they must be lost in time. So now it tells us that each and every one of these structures that loses stability actually has to be instantaneously unstable. So if I don't go all the way, I go almost all the way through, it immediately pops back. I have to overshoot and stay there for a fraction of a second, and then it stays for a short while. There's a graphic interpretation to now understand. I give you a geometry. Will it ever pop? So there's this elastic potential, which I remind you, it's not a potential system because we do lose energy, but instantaneously could think of these things. However, these springs, this point we have only moves up and down. We have L2, which is the rest length of this guy. We have L1, which is the rest length of this guy. So we have two parameters in the system, but we only change z. Okay? So if this is L2 and this is L1, there's an effective curve in space relating L1 and L2 along which the states of the system exist. Okay? L1 bar and L2 bar are what these lengths would like to be. Those are not constrained. Say I'm starting at rest, I'm starting here. L1 equals L1 bar, L2 equals L2 bar. This is the rest state. Okay? Now I bring the system to some other state, say L hold. I take this down there. The reference metric, L bar, starts evolving towards L hold. All I need to ask now is, does there exist a point on this curve which is closest to L bar at this instant in time? This depends strongly on the curvature of this curve, and only on that curvature. So now, in this case, you can show there's only one stable solution, and it's in here. Regardless of how long you hold this guy, it will never get stuck. This is what happens when you make these guys too thick. So regardless of how long I hold them in this state, they will never pop. I mean, they will never stay. There's the other limit. There's the guys that are actually too thin. They show bistability. So we start here. L1 equals L1 bar. L2 equals L2 bar. But now, to this point, there are two closest points. Locally, I mean. One is here. The other is here. So this point, locally, is the closest point on this curve to this. So if I bring my system to the other state here, it is actually stuck in there. Now what happens if I turn on this viscoelastic evolution? It only drags L bar towards me. It has absolutely no reason to get me out of this barrier. And then there's the interesting guy. The interesting guy is such that if L bar remains at the stationary, at the stress-free solution, then there's only one stable solution. It's only this guy that's stable. However, if I take it to the inverted state, and now I let it relax for a while, then I evolve along this line, say about here. It only depends on how long I held it and some material properties. Now from this point, there exist two solutions. One that's a perturbation of this guy, and another one that was never there to begin with, and I just made it. You can show, it's not evident from this figure, but you can show that this guy, in dynamics of L bar, must be lost. So all I showed you had to do with springs and dashpot. All the relaxation rates were exponential. Everything was very, very simple and linear. But it turns out it doesn't have to be this way. These guys don't have exponential relaxation. They have either logarithmic or small power laws relaxation. And you can absorb that by changing the dynamics of L bar to any general linear memory kernel you'd wish. So this is something you can measure and input into your theory. And then you could take this whole theory and make it three-dimensional tensorial. In general, every isotropic, incompressible, linear viscoelastic solid can have its dynamic written this way. This is the stress, this is the strain. The strain, just to emphasize, is a measure between distances. We measure distances using a metric. So this would prescribe the state of the system we're in. And we compare it to G bar naught, the way the system was prepared, was born, and what it would always wish to be. So this is an infinite memory of the system. This is find that if you just flip them, they immediately flip back. But if you wait even a fraction of a second, you will get a very, very long jumping time. So this is where you get the most simplification. And then we want to test the phase diagram. It turns out that the phase diagram does not depend at all on the dynamics. It depends on a single parameter, which is beta, which is the fraction of stress loss between t equals 0 and infinity. So we took this mold, cast about 50 different cones, and examined their phases. And for each and every one of them, you see that they lie exactly where the prediction says they would. These are stable ad infinitum. This are unstable regardless of how long you hold them. And each and every one of those that acquired stability and lost it in a finite time lies back where they should be. So to summarize, it is possible and actually insightful to describe viscoelastic solids through a temporally evolving rest method with respect to which instantaneous elastic strains are measured. And once you're able to describe systems through these more intuitive terms, then you have these geometric tools at your disposal, and it can show that specifically for incompressible isotropic linear viscoelastic solids in 2-3 dimensions, if you start from rest, viscoelasticity can never cause a stable solution to lose stability. If you see stability loss in these kind of systems, your system had to be unstable to begin with, or that it did not start at rest. Viscoelastic relaxation can acquire stability during time. However, we can also prove that such stabilities have to be lost at a finite time. Now, there are fairly stringent restrictions, such as the incompressibility and the fact that they have to do things abruptly. And you can also show that this theory is continuous in these restrictions, meaning that if you're not doing this really instantaneously, it takes you a finite amount of time to flip these things over. But you do it sufficiently fast, then most of these results still hold pretty well. Thank you.